popular approaches like LIME and SHAP are based on it. Therefore, the intention of this talk is to introduce you with a number of feature selection approaches and their trade-offs. So we can start today's session by asking the following questions. What are the different feature selection approaches? How evidential rule-based approach handle imbalanced classes? Does the evidential rule-based approach computationally expensive? Welcome. Hello, everyone, and thanks for joining us. My name is Rehman Zafar, and I am a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Dr. Fatima Almaghrabi. Dr. Fatima recently completed her PhD in Operations Research and Decision Sciences from Alliance Manchester Business School. She also completed her MBA and BSc in Management Information Systems from King Abdul Aziz University. Currently, she is a researcher at Alliance Manchester Business School and working on a research project titled Interpretable Feature Selection using the Evidential Reasoning Rule and Application on Healthcare. She is an experienced academic, which includes higher education teaching. She has acquired a variety of data analytical skills such as medical datasets analysis and programming in MATLAB and Python. She has published her research in multiple conference papers and peer-reviewed journals. Fatma will be presenting evidential reasoning rule-based feature selection. To the target audience, please post your questions in the chat and I will be asking your questions immediately after the presentation. So without further delay, I am now turning this presentation over to Fatima. Please take it away.
Hi everyone, my name is Fatima Almaghrabi. I will be talking today about my research in using the evidential reasoning rule for feature selection and the application on improving trauma outcome prediction. I would like to start by thanking this series of Aggregate Collect for inviting me to present and for this opportunity. So today I'm going to talk about variable reduction and feature selection, then the evidential reasoning rule for feature selection, and how the evidential reasoning rule can be implemented in this area. And then I'm going to talk about our most recent paper, an evidential reasoning rule-based feature selection for improving trauma outcome prediction. I'm going to talk about the case study, the results, and future work from this paper. And also I'm going to mention briefly another paper about a new interpretable machine learning technique for predicting traumatic injuries outcomes, which can be related to this paper, or another application for interpretable machine learning. So when we talk about variable reduction in today's world, with the introduction of big data and with the huge amount of data that has been collected and that is being collected every day in multiple fields, in healthcare, in finance, and other fields as well. This huge amount of data and a huge amount of variables that are collected to construct and build prediction models and create variables that can represent the actual data sets. Some of these variables, what we notice is that all of these variables are actually important, are relevant to the prediction models? Is there some redundancy, or are some of these variables are redundant? And can we actually choose some of these variables to construct a better model? And also, some of these variables might be irrelevant actually to the prediction. So for these two reasons mainly, and other reasons for selecting and constructing a more accurate prediction models and machine learning models, the field of feature selection and variable reduction provided the solution for finding and constructing models with the most relevant features. So variable or feature selection, it chooses some of the features or some of the variables to construct the model using the original variables, where dimensionality reduction is similar in terms of selecting the or building more accurate models and selecting the features with more accurate or more relevant to the prediction. However, with dimensionality reduction, it actually changes the original variables and takes some of the some percentage from each variable to construct a new set of variables for prediction. So, dimensionality reduction and feature selection both construct and select variables, more accurate and predictive variables, where feature selection algorithms keep the original set of variables in the prediction, which make it easier actually for practitioners and for system and decision-making models users to understand the set of variables that have been selected and to actually highlight them in the procedure of collecting the data. So, for example, for variable reduction, it can actually combine multiple variables in one or two variables and construct a new cluster or a new variable clustering to create a new set of variables. In terms of feature selection techniques, there are many feature selection techniques that have been introduced through the years. They have been categorized also using different categories. So one of the most common categories is that feature selection methods can be defined or can be categorized as filter methods, wrapper methods, and embedded methods. Where filter methods are methods that are they have been divided based on the way they calculate the process of calculating the feature selection and ranking the feature. The filter method, they use the relationship between the variable and the outcome, or between the set of variables and the outcome, and to construct and to rank the features importance. And they are divided to univariate methods and multivariate methods. Where one of they have multiple advantages, such as they are very they don't require a lot of computational time. However, they don't consider actually the interaction between the variables, and also they are not based on prediction models. So they are not actually based on the way the prediction model has been is being constructed or can be constructed. Some of these methods, such as ReliefF, and which I'm going to talk about in the presentation today, and also information gain making. The second category is wrapper methods. These methods, they try multiple set of a combination of variables. So they try either by adding one variable at a time to test their prediction and test their how accurate the model can be in predicting the outcome, or actually reducing the variables one at a time. And they can be categorized to the deterministic and randomized wrappers methods. They can produce more accurate results. However, they may require a lot of computational time. And also they are constructed before the prediction model can be constructed. And one of the example for that is best incremental ranked subset. The third category, and the category that is actually related to prediction models, is embedded method. So these methods, they calculate the feature selection and feature importance using or through the prediction models. While building the prediction model, these algorithms actually calculate and compute the importance for each variable during the process. And one of the most popular feature selection technique, embedded technique, is random forest, which actually calculates out-of-bag error and also the importance for each variable during the prediction, building the prediction model. So these are the three main themes, three main categories for feature selection techniques. And for each one of these categories, they have their own. They have multiple advantages and disadvantages. Uh, for today topic, I'm going to focus more on the embedded method and embedded methods that have been introduced in this paper, which is the evidential reasoning rule. So for the evidential reasoning rule, I'm going to talk a little bit about the evidential reasoning rule, and then I'm going to introduce and talk about how it has been implemented as a feature selection method. So, a lot of you is familiar with Bayesian rule in probability and how it can be used for calculating posterior probability. The evidential reasoning rule is an extension from Bayesian rule. The Mr. rule is also an extension from Bayesian rule, where they calculate and assign probability for the outcomes. The evidential reasoning rule is another extension for the Bayesian rule. In this extension, or in the evidential reasoning rule, it have two advantages, and it have two features. The first one is the evidential reasoning rule, when it assigns probability for a set of hypotheses and for a set of features or outcomes, it actually calculates two additional parameters. It combines evidence with weight and reliability. So the evidential reasoning rule introduced the evidence weight and evidence reliability to the model, which can be very helpful in terms of calculating and actually incorporating each weight for each one of these variables, and also reliability for each one of these variables. So, for example, if we want to construct a prediction model using the evidential reasoning rule, there are multiple variables in the model. Each one of these variables may have different importance and weight in the prediction. So the evidence weight in the evidential reasoning rule actually allow us to incorporate this parameter in the model. The reliability is very important in terms of combining data from multiple sources. So, for example, if we are combining data from multiple data sets, each one of these data sets have reliability, or we can assign reliability to each one of these data sets. So, when combining these data sets, the reliability parameter is very useful in determining reliability for each one of them. And the weight and reliability can be defined using expert judgment or opinion, and also through data. This is the first feature for the evidential reasoning rule. The second advantage, or the second feature for the evidential reasoning rule to Bayesian rule, is that it actually the probability is assigned to a set of hypotheses rather than to a singleton hypothesis. So these are the two features that actually explain the advantages, or explain the addition of the evidential reasoning rule. And Bayesian rule is a special case of the evidential reasoning rule, where when all of the evidence have the same weight and the same reliability. This is the evidential reasoning rule. When we want to actually calculate the importance for each one of these variables and the weight for each one of these variables in the prediction model. So the evidential reasoning rule have been implemented recently for classification and for prediction. So it can be used actually as a method for building a prediction model and an algorithm where each one of the features can be used as an evidence to predict the outcome. And one of the advantages that have been noticed using the evidential reasoning rule for classification is that it actually can handle missing data very well. And also, of course, it introduced weight and reliability in the model. which can actually improve the prediction accuracy as well. It has been used for classification. Now we're going to talk how the evidential reasoning rule can be used for feature selection. So as I explained, the weight here, the parameter, the weight parameter here represent how important each one of these evidence in building and in arriving to the outcome or to the prediction. So when we start with when we start the model, we assume that all of these variables have similar weights, but we can actually incorporate or combine the evidential reasoning rule with optimization and using a maximize objective function that maximizes the area under the curve, the AUC, which can actually maximizes the AUC by changing the weight and the importance for each one of these variables, which arrive to a set of weight for each one of these variables that represent the importance for these variables that can be assigned to arrive to the best or the highest AUC or prediction accuracy, depending on the performance measure that have been used or can be used in their classification. So combining the AR rule with optimization, we can actually train the model to assign various weight to each one of these variables that can actually arrive us to the highest or to the maximum AUC or area in the curve or any performance measure that can be used. And during the optimization, one of the conditions that I added was that the sum of the variables weight is equal to 1, which represent that the value for this weight can be from 0 until 1, whereas the sum of all of the variables weight is equal to 1. So this process explained how the ER rule, when combining with optimization, can actually provide us with a new set of weight for each one of these variables, for each one of variables in the model, that can actually give us the highest AUC, which represent how important each one of these variables in actually in the prediction model and to the field that has been implemented on. Now, after explaining the AR rule, I'm going to talk about the case study and paper where the application has been implemented. So in this paper, we talked about the application of the evidential reasoning rule for feature selection in trauma and the traumatic injuries. So trauma can be defined either of psychological trauma or traumatic injuries. So in this paper, we focused on traumatic injuries, which can be defined as any sudden and life-threatening physical injury, potential resulting in secondary complications such as shock, respiratory failure. Trauma is an important topic to be discussed and an important field to be to build multiple prediction models and to define the most important features to be calculated within the field, since it's a leading cause of mortality in the under 40 age group. It's important definitely to identify the most important variables and the most important features that are related to any severe outcome for patients with traumatic injuries. So when we actually build a better prediction model for trauma, we help define the set of factors that can actually help the practitioners to focus on to build and to make better decisions and to build better prediction models. So there has been some research in trauma feature selection. It's still there are still only a few research in trauma feature selection, and also the method that have been implemented are still some of the popular feature selection methods. So it's a research to explore. So these are some of the papers that have been published in feature selection for traumatic injuries prediction. Here are some of the here are these papers classified as the type of feature selection methods, either filters, wrappers, and embedded methods. I want to mention, as I said, it's still a field to explore and to add to explore more feature selection methods. One of the topics that can be discussed with prediction models, especially in fields in healthcare and fields where the outcome for the prediction is highly imbalanced. What I mean is, when we collect data for, like, for example, trauma or healthcare, usually the set of variables or the outcome would be a lot of patients would have a very normal outcome and without any severe or complexity in the following the injury. So what happens is, a lot of the data sets is focused on the people with the good outcome. Either, for example, we have people who stayed in the hospital, people who actually have been treated and didn't stay for a long time, or, for example, for a severe outcome or non-severe outcome, or, for example, a life or death. So usually it's a large group on one side, or a large group in one of the classes in the outcome. Why it's important to discuss this with feature selection? Because feature selection methods, the process of calculating the feature selection, it depends on the feature selection methods. Some of the feature selection methods actually calculate the feature importance based on the majority class. So, for example, in this case, for example, the non-severity group or the alive group. So the features that have been selected and ranked are based on the majority class, where we are actually considered and focus on both groups, the majority and the minority group, the severity group as well. Because if we want to define the group of people who might have a potential severity outcome, we would definitely want to know the set of variables that can be actually predict this outcome, or they can be correlated with this outcome. So from this point of view, it's important to consider the imbalance classes, or how these changes, how these imbalance in the outcome variable can actually affect the feature selection method, or can actually affect the outcome or the selected features. Previous research into imbalance classes with feature selection has implemented multiple methods for handling this issue. Most of them, they used a smooth, which is a method for creating synthetic examples from the minority group to be equal to the majority class. So it will be similar number of cases in both examples. The others, for example, can be decreasing the majority class in the outcome to make sure that both cases have similar number of cases in the prediction models and when calculating the feature selection. So these are some of the methods or the techniques that have been implemented. Also, most of these papers, especially when talking about imbalance classes, they focus also on the performance measure, because when we compute, for example, prediction accuracy with imbalance classes, prediction accuracy can be very sensitive to imbalance in the classes. For example, if we run the model and the prediction accuracy was 95%, and the actual classes, the majority class in the data set is 95%, that means that the accuracy or running the model would give us actually the same result as the percentage that we already know about the classes in the data set. While there are many other performance measures that they are less sensitive to imbalance classes, such as the area under the curve or the AUC. So most of the topic today, I'm going to discuss more about the AUC and the application of the AUC in using the AUC as a performance measure. Other methods as well as J-mean, it can be used, or also F measure. So this in terms of imbalance classes. So we talked about implementing the ER rule. We talked about considering the imbalance classes issue in with feature selection. Now we're going to talk about how the procedure of running these methods in the paper has been implemented. So in the paper, we used input data, data normalization, and then cross-validation to classify the data, or to create 30 data sets, training and testing data sets. Then we have two groups of data for data: the imbalance data, the normal data that has more a majority class. And for this data set, we run multiple feature selection method, the AR rule, and other two feature selection method that has been implemented previously with trauma data. And for the balanced data set, we applied smooth to the training data to create more synthetic examples from the minority class to create more a balanced data set. After balancing this data set, we ran feature selection, the same feature selection methods and algorithms using this data set. And for the outcome from both models, or both the outcome for both feature selection methods for imbalance and balanced data, we ran we actually created 5 prediction models for each data set. So for example, for the AR rule, we created multiple for the 10 first important feature, the 20, the 30, the 40, and the 50, the whole data set. We created multiple prediction models to test which one of these feature selection methods actually can give us or can actually select the most relevant variables in the prediction. And for example, the method that can actually select or create, for example, the first 10 feature features prediction model with the highest AUC, for example, would be, of course, better in determining the most important features. So created 5 prediction models for each data set, and running support vector machine as a machine learning algorithms to do the prediction using the rank feature. Also, the ranked features were added to the Spearman rank correlation coefficient and using p-value to see the ranked features, are they similar between the balanced data or the imbalanced data for all of the feature selection methods. So is it actually for each one of these feature selection methods, do they actually or do the imbalance in the classes actually affect the selected features? And does these features, or does this feature selection method actually focuses only on the majority class or both classes? So this is the feature selection process that has been implemented in the paper. And now I'm going to present and talk more about the case study and the results. So the feature selection methods that have been implemented, the evidential reasoning rule that I talked about, random forest, which is an embedded technique calculating the importance for each feature during the prediction process, and the importance range starts from 0 and above. So it starts from 0 actually. And for the ReliefF algorithm, It's a filter method. It has been implemented previously using in one of the papers in trauma prediction. And the feature weight provided by the ReliefF algorithm ranges from -1 to 1. So there is a specific range for the importance and the weight for each one of the variables. So the 3 feature selection methods have been implemented to do the prediction. And now we're going to discuss the case study and the variables. So to implement these 3 feature selection algorithms, we use traumatic injuries or trauma patients data set from 2012 to 2015, all patients irrespective of age. So for all age groups, they arrived at any hospital in England or Wales. And the number of features that have been used in this case study is 50 various demographic and medical features for feature selection. So we're going to rank these 50 features to see which one of these 50 features is actually relevant and actually can give us a very better prediction models. So in terms of the AR rule optimization results, if you can see, here on the right, these are the ranking for the weight for each one of the variables from 1 to 50. The blue color represents the variable importance, and the red color represents the variable importance after balancing the classes using smooth. If you remember here, we have the balanced data and the imbalanced data, and we use smooth for the training data. So the blue color represents the variable importance for the whole data set, the imbalanced data set, and then the red one represents the variable importance. As you can see, there are some changes. For example, the GC Glasgow Coma scale, it's a medical score. It's very important. It shows very important with the majority class, but still it's an important variable with balanced classes. So there are some changes with the importance for the features, but some of the variables actually provided similar importance, either with imbalance or balanced classes, for example, like operation number. So this is the optimization feature. Now, after running support vector machine for multiple models, we have 50 features here. We selected the highest 10 features, for example, this one, this one, this one, this one, and this one, for example. So for the highest 10 features, if we run the model for the highest 10 features using that have been selected by the ER rule, we can see this is the AUC for the results, and this represents the mean for the results. And the mean starts from 0.895, and going until 50 feature, adding 50 feature, which arrived to around 0.92. So the difference actually is not much from 0.895 until 0.92. We will see the other algorithms, how the results will be. So this is for the ER rule optimization result. These number or these selected features were based on the variable importance, the first variable importance. So this is for the ER. This one is for the ReliefF algorithm results. These are the importance of the feature. As we can see here, most of the features are important, but not all of the features are actually important. Some of the features are actually degrading the model. So that's why it's definitely important to select and run feature selection to define and find the most relevant features. So as we can see here, for example, the operation number here is not very relevant feature. We can see here also vehicle protection, valid vehicle protection. It's not very relevant, but because not a lot of the patient actually, one of the reasons this one is not very relevant in this model is because not a lot of the injuries here were actually based on vehicles. So not a lot of the patients were in vehicles. So the results for the variable importance for the impedance and the balance data sets. And here we have the results for the running the SVM, support vector machine. As we can see, the algorithm didn't provide us with very accurate features. For example, it will start for the 10 features from 0.83. And there is also, after 30 features, there is a huge difference between the 30 and 40 features. The 40 features is around the 50, which is 0.92. So this difference in the selection, and also this difference in the prediction or AUC results shows that the results from the ReliefF might not be very useful at the beginning. The 40 variables feature is very so in terms of selecting and identifying the 40 variables in the model, it was very good, but before that it wasn't. It didn't provide very good results. So in terms of random forest, the third algorithm, it provided, as we said, it gives a result or score starting from 0. These are the results for the features, importance for the imbalance and the balance data sets. And these are the results for the prediction. Still, the ER rule results start better from here. So for the 10 model in the ER rule start from here, the mean for the models, where in the random forest starts from 0.885. Then the 20, 30, and 40 variables are a bit similar from 0.9 until 0.91. And then finally, the 50 variables, all the variables model, it's similar to other models. So as we can see, selecting the most important features, we're predicting using the most important features that have been selected by the ER rule, provided the highest or the better prediction accuracy using the AUC. Okay, now we can see that feature importance, it was the results for feature importance. A very important question is, were there any features that have been selected by the three algorithms, and where actually the AI rule actually provided us with a very good set of features. Here, it shows the 10 highest or relevant features selected by the three algorithms. Here for the ER rule and their score, the ReliefF and their score, and the random forest and their score. And as we can see, length of stay, Glasgow Coma Scale, the injury severity score, Ward 2, and length of stay in the intensive care unit were selected actually by the three algorithms. So it shows that the ER rule actually can select the most important variables, and not only that, but also provided a very good, the selected variables provided very good and more accurate prediction models. Also, we're going to discuss more about these selected variables. For example, length of stay and length of stay in ICU. What they notice is that the more the patients stay in the hospital, the more they, for example, the more their situation will be settled, and they are not severe anymore. And also, of course, the people who are actually have a very mild injury, they will be they won't be stay for long in the hospital. The other two things that we notice here is that two of these selected features were the Glasgow Coma Scale and the injury severity score, which are a medical score, and they are very important to identify actually the severity of the patient. So it's the result that represent how the result can be actually can represent an accurate set of features, or a good representation of a real important features in the in real life example. More explanation, you can find more explanation about these features as well in the paper. The highlighted results shows that some of the features were selected to be the most relevant for the classification by the 3 feature selection technique. They shown to be more relevant to the prediction, and they are very important to the prediction, and they can select the most important and they can predict the model more accurately. There are also some consistency regarding the least influential factors. The least important variables were a lot similar between the 3 techniques. The imbalance in the classes, this is the second issue that we talked about. The imbalance in the classes actually affected the results in 2 implemented techniques, the AI rule and the ReliefF technique, which shows that it's good to consider the imbalance in the classes in the feature selection to see how the implementation of the method can actually does it actually represent both classes, or if it has multiple classes in the outcome, each one of these classes in the outcome, either it has a large group in the outcome, or other groups as well. It can be concluded also the feature selection result obtained by the AI rule constructed a more accurate model in terms of the 10 most important features, and improved performance and prediction performance with fewer important variables. Okay, so now we talked about the results and the highlighted result and the discussion. Some of the future work and directions from this paper would be to actually customize the prediction models and the feature selection for each severity level. In trauma, trauma patient usually categorized to mild, moderate, and severe group, and for each one of these groups there would be some relevant features. So for example, length of stay would be more relevant, for example, to moderate and severe group, whereas the mild injury, they won't be, for example, staying in the hospital for a long time. So defining each one of these severity level for patients can actually help build various feature selections and create or identify the key features for each one of these groups. Also, future research would include expert judgment and expert subjective opinions about the feature, and to add more human-in-loop judgment on the selected features and building the prediction models. Also, from what we noticed, medical scores such as the GCS and the ISS are very relevant and very important in the prediction models. So future work regarding trauma would encourage incorporating more trauma score or trauma medical scores such as injury severity score and the revised trauma score RTS. So today I talked about variable reduction and feature selection. What do we mean by feature selection? Also, the evidential reasoning rule for feature selection. The evidential reasoning rule with feature selection, our recent paper for improving trauma outcome prediction, a case study on trauma and explaining the case study, the main result, future work, and also I'm going to mention a little bit about a new interpretable machine learning technique for predicting traumatic injuries outcomes based on vital signs. These are some of the references that have been used in the presentation. And in terms of the new interpretable machine learning technique, you can find more about it in the paper provided in the references, where it talk about using the evidential reasoning rule or a new framework which called the MAKER, the maximum likelihood evidential reasoning, to combine evidence with to combine independent evidence or dependent evidence. So when we talked about the AI rule, we talked about the two parameters, the evidence weight and evidence reliability. The Maker framework introduced a new dimension, a new parameter, which is the interdependency index, to combine dependent evidence actually in the prediction model. So we talked about building an interpretable machine learning technique using the Maker framework in this paper, and this is the main framework for the paper. You can read more about it in this paper as well. Thank you very much for listening, and thank you very much for joining the series today. I would be pleased to hear your questions.
Thank you, Fatima. Now we are starting the Q&A part of the session with live questions as well as questions we had received in advance. So the first question is how the impact of imbalanced classes in feature selection is measured.
The impact of imbalanced classes is measured. Okay, yes. So in terms of measuring the impact of the balanced classes, it can be explained in this here. We use Spearman rank correlation coefficient to measure how changing the features is the features are similar between the balanced and the imbalanced classes.
Thank you.
So yeah.
Yeah, go ahead.
Yes, so the Spearman rank correlation coefficient has been used for that purpose.
All right, thank you. And the next question is how comparable is the performance of the ER rule to some of the previous feature selection techniques?
Thank you very much for this question. It's an important question. It shows from the results here for the imbalanced data set. The ER rule actually showed very good and consistent performance measure using the AUC, of course. So here with the highest 10 selected feature, if you chose the 10 selected features or key features from the three methods, we see that the ER rule has the highest AUC results.
Okay, thank you. And the next question is, are the differences in the selected features statistically significant?
It shows, yes, it shows that there is some significance in the results between some of the feature selection algorithms. Yes.
So what is the optimal set of features that has high prediction performance with the least number of variables?
That's a very good question. Thank you very much. It's definitely depending on the expert and the user for the models. As we saw here, for example, if we wanted to select the highest 10 features, the ER rule actually provided us with the best results. So since most of these algorithms actually calculate the feature selection using by ranking the features, so choosing the number of features would definitely depend on the ranked features. Also, as we noticed, there is, for example, there might be some changes in the accuracy. So here we run multiple models using the 10, 20, 30, 40, and 50 features. And we notice, for example, the 10 features or the 10 variable would be very good results. But for example, there will be some changes between, for example, the 30 and 40 here, and here the results also show higher differences in the results. So based on the results that we see for feature selection, based on the results that we see, if we find that the 10 selected features here, for example, if we want to choose the 5 most important features, the 10 most important features, if we found that these features are actually with this small number or with this number of feature, we can actually get very good results. In that sense, then we would definitely they would select this number of feature. If we can add more, then we can add also more and more features until we arrive to the trade-off between this is a very good number of features, and also the accuracy is very good, and there is not very much change between this number of features and the whole number of features. So in terms of the feature selection method that use ranking, it can be implemented by running multiple algorithms to see to see the various prediction accuracy, and to see the trade-off between the number of variables and the prediction accuracy.
All right. Thank you. Is there any trade-off between prediction accuracy and the number of variables of each technique?
That that's a very good question as well. Thank you very much. For each one of these techniques, it shows a trade-off between the results. For example, for the ER rule, we can see that between 10 and 50, there's only a change between 0.895 until 0.92. So it's very it's not very significant. It's very we can achieve very good AUC with only 10 variables. We can see here, for example, for the ReliefF algorithm, the 40 and the 50 variables have very similar AUC results. So in terms of the ReliefF, choosing 40 variable would be definitely better because it will give us similar AUC actually with less variables. In terms of the random forest, the change between 0.885 and 0.92, it's a bit of change, but we can see that, for example, 20, 30, and 40, it have similar results between 0.9 and 0.905. So for the user for this algorithm, choosing 20 variable would be better because it will provide a very similar results to 30 and 40 variables as well. So these are some of the examples for the trade-off between the AUC and the number of variables based on the technique and based on the algorithm that can be implemented.
All right. Is ER rule-based approaches are computationally expensive?
It's very. I would say it depends on the number of variables, but it's very the time to obtain the result is very reasonable as well.
Yeah, okay. So as compared to other well-known like random forest or any relief relief filter based. So what do you think? Is it more time efficient or time consuming?
It will well, that's an important question, definitely. It will take more time since the for example, the ReliefF algorithm only calculate the correlation between the variable and the outcome, so it doesn't actually calculate the interaction and doesn't calculate also the prediction while the prediction. So it's understandable that the AR rule actually would actually take more time, would consume more time. Yes.
Thank you. Okay, so the last question is how AR rule is capable of addressing the uncertainty in data that arises due to randomness, ambiguity, and inaccuracy?
That's a very good question. Thank you very much. The ER rule, actually, this is one of the advantages for using the ER rule. The ER rule and the way it calculates the prediction and the feature selection, and as mentioned and showed by previous research and this paper, it actually consider the uncertainty and ambiguity in data when calculating the prediction and when calculating the feature selection due to the probability that assigned to the evidence. So this is one of the advantages of the ER rule in classification, in feature selection, and also in handling missing data.
All right, thank you. Is your research open source or it is just not available on the internet, like the source code of this approach?
Uh, the paper is available. It has been published in Applied Soft Computing Journal. The code is not published yet.
Okay, thank you.
Thank you very much for the question.
And before we wrap up, are there any final thoughts that you would like to share with us?
Uh, First, thank you very much for all of the questions and for everyone asked questions. These are very insightful and good questions. I would like to add that the potential for the evidential reasoning rule for feature selection for classification is a good and a new area to explore. The applications can be implemented actually not only in healthcare applications but also in various data sets and in multiple applications in finance and in also other aspects, and also it can be very useful in terms of handling uncertainty in data set and handling missing data as well. So there is a lot of potential in terms of the method and the application of this area, and building an interpretable machine learning models as well.
Fatma, I congratulate you on a significant contribution to the field, and I thank you for a great presentation. And we thank all who joined us online. To see more free content like this, please visit our website at ai.science and log in to access slides from this and other sessions. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.
Thank you very much.